Combinations. This is a little bit different than a permutation. A combination is an arrangement of things, but the order is not important. So rather than an arrangement, I like calling these groups, because a group is just a cluster of things, and it's not a line, it's not an arrangement, it's not like a seating chart. There's not anything important about how you view them. And again, this has a similar calculator notation, NCR. C stands for combinations. Alright, and it has a little bit different equation. It's n factorial over n minus r factorial, just like the permutation, but you include divided by r factorial. So since we're dividing by another number, that assumes that there are less combinations than permutations. Let me show you why. So if I take the letters A, B, C and I arrange them in a line, I can arrange them 6 different ways. And I would take the calculation of 6 or 3p3 and get a total of 6 from that. If I take the letters A, B, C and put the 3 letters into a group, these are all groups of those 3 letters, but in that group, if I don't concern myself with the arrangement of the 3 letters, those 3 letters are in the group regardless of the arrangement they're in. So there's only one combination of these 3 letters. If I go 3C3, then I only get 1. And we can prove that on the calculator. Let's just go ahead and do that. So I say 3, hit math, again go to probability, here's C right under P, and 3, hit enter, and there's my 1. So order and non-order are going to be very important for these different types of items. Let's go through a couple examples. How many different committees? Okay, so a committee is a group of people, and as I said before, combinations are more like groups. 5 people can be chosen from 10 people. So this is really from these 10 people, I'm going to choose 5. And if I put this in a calculator, this is really hard to diagram out, as you can imagine. So I just go ahead and use a calculator for all these combinations. So I say 10, hit my math, probability, hit that 3, and I want to choose from 5 people, and I get 252. So here we go. You got 6 friends and they want to play enough games of chess to be sure that everyone plays everybody else, and you want to know how many games they're going to play. So in this problem, we're taking from 6 people, and since only 2 people can play chess at a time, we're picking 2. So we hit 6C2, and we get 15 different games. Now, one of the things you need to know is this combination method, combinations take out all repeats. So in the case where I showed you earlier, when we had our example, these are all repeated groups, all right? And the combination calculation takes all those guys out. So let's move to our next example. We want to determine whether each of these is either a permutation or if it's a combination. So we want to select 3 students to attend a conference in Washington, D.C. There's no hierarchy, there's no specific like titles for these kids, so we're basically picking a group of 3. This is a combination. Selecting a lead and an understudy for a play. There's certainly titles associated with these two, so order is going to matter. So this is a permutation. Assigning students their seats on the first day of school. This is more than just a general grouping because there is order to the seats, so this is also a permutation. This problem is a little bit more difficult. This is going to involve not only grouping, but a actual counting principle as well. 2 different events are going to happen. So let's read this. There's 14 juniors, 23 seniors, and a service club. The club is to send 4 representatives to the state conference. If we were to just pick a group of 4, not a problem. We add all these up, 14 and 23, choose 4, be done. But it asks, how many different ways are there to select groups of 4 to attend? Well, that's what I'm talking about. So we add these up. We have 14, 23, total of 37. We're going to choose 4. That's totally straightforward. So if I go 37, choose 4, not a problem. Go to my calculator, shoot on over to probability, get a fairly large number, 66,045. But now is the harder part of this problem. Now they decide, rather than just choosing 4 kids, they want to make sure things are kind of equal and they represent 2 juniors and 2 seniors. How many different groups are possible? So what we really have to do is we have to have 2 events. Event 1 and then event 2. This is going to be choosing a group of juniors and then choosing a group of seniors. So in order to choose a group of juniors, we have to ensure that we get a junior. So I can't pick from 37. I have to take from my 14 to ensure a junior, and I only get to pick 2 of them. Then, to ensure a senior, I have to pick from my 23 seniors, and again I have to pick 2 of them. 2 different events, this many ways to do the juniors, this many ways to do the seniors, multiply together to get my total of different ways. So we can do this on our calculator as well. Make sure you use parentheses. We go 14, C2, and 23, C2, multiply those guys together, and we end up with 23,023 ways. So the last one is a little more difficult. The big deal about today was A, making sure you understand what a counting principle is. Lots of different choices, multiply them together, and then understanding the difference between permutations and combinations is basically order and non-order.